The romanticized fantasy of the tactical bunker collapses the exact moment it meets the unyielding math of structural engineering. 93% of self-built survival shelters are not defensive strongholds. They are structurally compromised traps waiting for a single catalytic event to trigger their catastrophic failure. Most civilian preppers design subterranean layouts based on cinematic tropes, military surplus manuals, and video game geometry rather than the cold realities of hydrostatic pressure, thermodynamics, and soil mechanics. Today, we dismantle the 7 most common tactical shelter layouts that fail under real-world physics, exposing the hidden architectural flaws that turn steel and reinforced concrete into liabilities. Before we analyze the structural formulas, you must understand a critical invisible threat, a design flaw present in almost every layout that silently weaponizes your own breathing against you long before an external enemy ever reaches your perimeter. It is an engineering oversight so insidious that it ensures a slow death, and we will dissect and correct it later in this protocol. We begin with Layout 1, the linear dead-end corridor. This design positions the primary living quarters at the absolute termination point of a single straight subterranean hallway. Amateurs choose this configuration because they believe it creates an unbreachable fatal funnel, allowing a single defender to hold off multiple intruders. Physics dictates a different, lethal reality. When an external kinetic impact or an explosive charge is introduced at the entrance, it generates a high-velocity blast wave. In an open-air environment, this wave dissipates radially. However, in a straight, smooth-walled corridor with parallel surfaces, the overpressure wave undergoes severe wave confinement. Restricted by the walls, the kinetic and acoustic energy compresses into a tight, planar shock wave that actually accelerates as it travels down the hallway. Because there are no expansion chambers, baffle walls, or 90-degree deflection angles to disrupt the energy vector, the shock wave hits the terminal living quarters at maximum velocity. The pressure spikes instantly, causing immediate barotrauma. This ruptures the eardrums, destroys delicate alveolar lung tissue, and causes fatal internal hemorrhaging to anyone inside without a single fragment of shrapnel ever entering the room. Furthermore, from a structural safety standpoint, a single localized ceiling collapse or structural compromise at the entry point permanently seals the occupants in a subterranean tomb with 0 alternative paths of egress. Layout 2 introduces the double-decker vertical stack. To minimize the horizontal excavation footprint and reduce surface visibility, this layout places storage, heavy machinery, and water tanks on a lower level directly beneath the primary living quarters. This layout completely ignores the foundational mechanics of soil load-bearing capacity and deep water table mechanics. Excavating twice as deep to accommodate stacked vertical levels exponentially increases the lateral earth pressure and hydrostatic forces acting on the lower structure. Subterranean soil pressure does not scale linearly. It compounds with depth due to the weight of the soil column above. Unless the bottom floor is engineered with an incredibly thick, heavily reinforced poured-in-place concrete slab tied into deep subterranean anchors, the upward buoyant force of the water table will eventually exceed the dead weight of the structure. This triggers foundation heave, cracking the concrete floors from the bottom up and allowing high-pressure groundwater to breach the moisture barrier. Simultaneously, this design creates an internal structural crisis. The concentrated weight of the upper living quarters, furniture, and occupants exerts a massive, continuous downward load onto the lower level's structural support beams. This creates a severe bending moment at mid-span, leading to structural fatigue. Under the minor seismic vibrations of a nearby surface impact, these overstressed beams will snap, causing a total floor collapse. Layout 3 is the modular hexagonal hive. This layout utilizes interconnected prefabricated pods, often modified shipping containers or modular steel cells, arranged in a geometric honeycomb pattern. It is highly praised in modern architectural software because it allows for modular, step-by-step expansion. However, the physics of joinery and soil shear mechanics render this layout highly unstable over time. Every connection collar between 2 independent pods represents a localized point of structural vulnerability. Soil is not static, predictable medium. It behaves like a highly viscous fluid over long periods, shifting, expanding, and contracting based on localized moisture saturation and seasonal temperature gradients. As the Earth moves, it exerts uneven, multi-directional shear stress across the segmented Hive structure. Without a continuous, monolithic concrete foundation to absorb and distribute these forces evenly, the joints settle at different rates, a phenomenon known as differential settlement. This movement buckles the connection collars, shearing heavy mechanical fasteners and tearing through outer waterproof membranes. Once the structural seal is broken, high-pressure subterranean moisture infiltrates the electrical conduits, causing cascading short circuits that will neutralize your primary power grid within hours. Layout 4 presents the Perimeter Trench Outpost. This is a semi-subterranean layout featuring a central living hub surrounded by a defensive ring of reinforced trenches, fighting positions, and firing steps designed to provide comprehensive 360-degree security and surface awareness. This configuration fails fundamentally against fluid dynamics and thermodynamic visibility. During a prolonged storm or flooding event, heavy rainfall converts the entire perimeter trench system into an accidental, artificial drainage ditch. Because the trenches encircle the structure, the water channels directly towards the foundational walls of the central hub, rather than away from it. Water pools at the base, completely saturating the load-bearing soil. This saturation induces soil liquefaction, stripping the earth of its structural integrity and causing the central hub to tilt, crack, and sink into its own foundation. Externally, the excavation of the trenches permanently alters the natural contours and thermal mass of the landscape. The trapped water and disturbed soil densities hold heat differently than the surrounding undisturbed terrain. To any modern thermal imaging system, airborne drone reconnaissance array, or satellite multispectral sensor, this altered thermal dissipation pattern glows brightly against the natural background, rendering your hidden position entirely obsolete. Layout 5 is the High Ground Observation Redoubt. This layout places the primary shelter directly atop a prominent ridgeline, hilltop, or cliff face to maximize lines of sight, establish dominant tactical positioning, and control the high ground. This layout violates basic atmospheric fluid dynamics and ballistic physics. High ground positions bear the brunt of maximum velocity wind loads, exposing the above-ground elements of the structure to continuous dynamic pressure and requiring massive structural engineering just to withstand standard atmospheric storms. More critically, positioning a structure on a ridgeline creates a stark silhouette against the sky, turning it into an undeniable geographic marker. Ballistically, the tactical advantage of the high ground is an illusion when dealing with modern optics and trajectories. An attacker firing upward from a lower elevation benefits from a trajectory that crosses through expanding, less dense air layers over short distances. Conversely, the defender must contend with severe updrafts, crosswinds cutting across the cliff face, and angle glare that distorts target acquisition. By prioritizing a wide view, this layout transforms your survival asset into an easily targeted, highly exposed geographic anchor point. Layout 6 involves the integrated vehicular bay. This design incorporates a garage, generator room, or mechanical workshop inside the primary sealed perimeter of the shelter for rapid deployment, vehicle protection, and immediate maintenance access without exposing personnel to the surface. This layout fails catastrophically due to fluid dynamics, thermal expansion, and gaseous stratification. Internal combustion engines, fuel storage cells, and recharging battery banks continuously off-gas carbon monoxide, nitrous oxides, hydrogen gas, and volatile organic compounds. Because these toxic gases have varying molecular weights, they do not mix or dissipate uniformly. Instead, they settle into distinct atmospheric layers. Carbon monoxide possesses a molecular weight nearly identical to clean air, meaning it does not rise to the ceiling or sink to the floor. Instead, it diffuses completely throughout the entire space, completely bypassing low floor or high ceiling exhaust ports. It silently bleeds into the adjacent living quarters through unsealed cable conduits, door frames, and microscopic structural shifts. Without a completely independent, hermetically sealed pressure boundary and a dedicated, isolated air handling system, the integrated vehicle bay slowly converts your entire living space into a highly efficient, lethal gas chamber. Layout 7 is the perimeter wall overload. This is a design where the external, heavily reinforced concrete walls meant to withstand kinetic impacts or explosions are simultaneously used as the primary load-bearing columns supporting the weight of the shelter's heavy overhead roof slab. This represents a fatal consolidation of architectural roles. A core tenet of defensive engineering is the absolute separation of the outer kinetic barrier from the internal structural frame. When an external kinetic impact, such as a heavy vehicle ramming, a falling boulder, or an explosive blast, strikes an integrated perimeter wall, the immense energy is not deflected. Instead, the kinetic energy transfers directly through the vertical concrete columns and into the overhead roof. The resulting structural deflection causes immediate lateral displacement of the roof support beams. Deprived of its vertical equilibrium, the massive overhead concrete slab shears at its anchors. This brings thousands of pounds of reinforced concrete collapsing down into the living space below, crushing the occupants and destroying all life support infrastructure instantly. This brings us back to the universal invisible threat highlighted at the beginning of this protocol: atmospheric stagnation and moisture condensation. In all 7 of these structurally flawed layouts, designers consistently fail to calculate the moisture output of the human body. A single human adult releases approximately 40 grams of water vapor into the air every single hour through simple respiration and metabolic sweat. Multiply this by several occupants over an extended period, and you are introducing liters of liquid water into a completely sealed system. In an enclosed, uninsulated subterranean space surrounded by cold earth, this airborne moisture instantly condenses on the interior surfaces of the concrete or steel walls. This creates a high humidity environment that corrodes exposed electronics, short-circuits power lines, and fosters the rapid, unchecked growth of toxic black mold spores, rendering the air unbreathable within days. To survive real-world physics, a shelter layout must abandon these geometric traps and deploy an active thermodynamic barrier. This requires a dual-wall design where a continuous insulated airspace must be engineered between the outer structural earth retaining wall and a completely independent, vapor-sealed interior living envelope. This ensures that the cold, damp temperature of the Earth never comes into contact with the warm air of the living space, eliminating condensation entirely. This dual-wall design must be combined with a positive pressure multi-stage filtration system. Air must be forced to move in a continuous, one-way circuit, entering through high-level chemical, biological, radiological, and nuclear filters into the living quarters, flowing downward into a low-point drainage sump to capture heavier toxic gases, and finally venting safely to the surface through a dedicated blast valve exhaust. This architectural loop prevents moisture accumulation, eliminates toxic gas stratification, neutralizes blast wave vectors, and ensures the interior atmosphere remains completely breathable during extended lockouts. Protocol observed. Knowledge retained.